Hello everyone, and this is an introduction to cosmology. Cosmology is the study of the universe as a whole. The universe is everything that exists, and another word for it is the cosmos. I want to say at the top of this video that if this is your first time looking at this subject, then there are a lot of things in cosmology that are very strange to think about. This is normal, and if you have trouble processing some of this the first time you hear it, don't worry, everyone does. The plan is to look very quickly at the universe from the Big Bang to the solar system, at least as far as we know. I will go a little bit into how we know this, but only in simple terms. There is much more to look at beyond this video. The Big Bang is the formal name for scientists' model of the beginning of time. But remember that time is part of our model of physics, and before the Big Bang, our model of physics didn't work. So we can't say for certain that the Big Bang was the beginning of everything, but we are certain that it is the beginning of time as we understand it in physics. But the Big Bang was 13.7 billion years ago, so physics is doing pretty well as a model. What is the Big Bang? Well, it may have been an expansion from some kind of fluctuation or bubble. A bubble of possibility, which was suddenly able to become a reality for some reason. And this led somehow to a sudden expansion. All energy and space was created from a single point in a single instant, and this origin point for the expansion is called a singularity. But there's nowhere in the universe now which is the point of the singularity. All of space was there at the beginning, and all of space is still there now. It's just a lot more spread out. You can see what I mean. Some of these ideas can be a little mind-bending, and I invite you to go with it for now and try and build your understanding more over time. There are a couple of common misconceptions we need to clear up about the Big Bang. Number one, the Big Bang was not an explosion. It's natural to think of it like an explosion. It was very hot and it expanded very quickly. This certainly sounds like an explosion, but in reality, what was happening was the universe was very small, but all the matter and energy was contained. A lot of matter and energy in a very small space is very, very hot, and it wants to expand. But all that matter and energy stays contained. So the Big Bang was not like a popping balloon and all the air and energy bursting out. It's more like a balloon being blown up. The rubber in the balloon gets bigger, but there is still the same amount of rubber and it is still one object. To make this metaphor work, we need to have a sealed balloon with a compressed air canister in it, so all the energy is inside the balloon at the start. The second misconception is that, like we said above, the singularity was not somewhere in space. Space and time began with the Big Bang. There was no space or time before that. So, as I said above, there is nowhere you can go in the universe today and say, this is where it started. That place is everywhere. People sometimes ask, what is the universe expanding into? If there was or is anything outside the singularity, we don't know anything about it. And we are fairly sure that we can't know anything about it. Maybe we will have some better ideas one day. There are a few theories, but there's nothing that's been seriously proven. In the same way, the Big Bang is also the start of time, in the sense that we understand time. It was t equals 0. Saying that does not fail when we ask questions like what happened before the Big Bang? Clearly, there is a possibility of something that led to the event, but for the purposes of any physics calculations, the Big Bang was the start of time, t equals 0. Anything that happened before t equals 0 is, scientifically speaking, a guess, at least for now. Speaking of time, we divide our ideas of cosmologic time into epochs or epochs. An epoch is a period when the universe is in a certain state. Maybe a certain type of energy or maybe particles dominates the picture. A new epoch signifies some massive change in the overall state of the universe. Let's look now at a quick timeline of the Big Bang. The Big Bang was the beginning, which we call t equals 0. Then there is the Planck epoch, and physics is still unable to work in this time because the Planck time is in the order of 10 to the minus 43 seconds. Any time shorter than that cannot be analysed with physics. Then we come to the Grand Unification epoch, where all the forces we now know were combined into one force because of the intense conditions at that time. We have some working theories of how to unify all the forces, but there are still some things we do not understand. After the Grand Unification epoch came the Inflationary epoch, when the strong nuclear force split off from the other forces, and this triggered, we think, a massive expansion to a size of around 84 million light-years across the whole universe. Following the Inflationary epoch was the Electroweak epoch, when gravity first separated from the unified force. And then came the Quark epoch, the electroweak force now divided into the weak force and the electromagnetic force. And these are the four major forces that we understand today. The universe at this time is called a quark-gluon plasma, and there are many subatomic particles flying around in this hot, dense state. Finally, the quarks begin to come together to form protons. They begin to form hydrogen nuclei. A proton is a kind of hadron, and so we entered the hadron epoch, where protons, later joined by neutrons, dominated the universe. So how long do you think all of this took? Seriously, just pause the video and make a guess. Are you ready? All of these epochs took about 1 second. That's right, all of those epochs happened in the first second of the universe. The Big Bang was t equals 0. The Planck epoch was in the order of 10 to the minus 43 seconds. The Grand Unification epoch came at around 10 to the minus 36 seconds. And we should not skip over the Inflationary epoch, where the universe expanded to 84 million light-years across in around 10 to the minus 32 seconds. This is obviously much faster than the speed of light, but the speed of light is only a speed limit for moving around inside space. There are no rules that we know of on how fast space itself can expand. So by the time we get to the end of the Quark epoch, we are in the order of 10 to the minus 3 seconds, which is a more everyday measure of time. Olympic races are timed to this level of accuracy. By the end of the Hadron epoch, we are at t equals 1. Around that time, there was a lot of destruction going on. In the early universe, there was matter and antimatter. When these two come together, they are both completely destroyed, which we call annihilating. For some reason, there was slightly more matter than antimatter in the early universe, and we don't really know why. But that is the only reason why there is any matter in the universe to make us and everything else we see. Otherwise, the universe would be pure energy. This is just one of the things we don't know about how we got to now. After the Hadron epoch, we come to the cosmic dark ages, from around 3 minutes, t equals 180, until around 400,000 years, T equals 10 to the 13. So they lasted for quite a while. This was a time when photons existed, but because everything was still so hot, photons were part of an interacting plasma and they were bouncing off everything and not able to travel very far. So we couldn't use photons to see by, even if there were any people at that time to see anything. This is why they were called the Dark Ages. It was not yet possible to see using light. After the Dark Ages, we are at around 10 to the 5 years after the Big Bang, and at this point the universe had cooled enough to allow hydrogen and helium nuclei to capture electrons so they could form the very first atoms. Matter as we see it every day now existed, although in the beginning it was only hydrogen and helium. This is called the epoch of recombination, when the electrons were captured and combined with the protons and neutrons to make atoms. Now, photons could travel through the universe as light. Many photons from that time are still traveling, and that is something we can detect. We call it the cosmic microwave background, or cosmic background radiation. And, for example, some of the static on your TV screen when you get that grey fuzz is at least partly caused by the cosmic microwave background. As I said, at first the universe was simply hydrogen and helium, but with a universe of atoms, gravity started to have a stronger effect. It started to pull hydrogen and helium atoms together, and more atoms in one place had more gravity, so they pull in more atoms. At last, there was so much density at the center of this cloud of hydrogen that a nuclear reaction ignited, and that caused the very first star to be born. It was not alone for long. All over the universe, hydrogen was clumping together, and its gravity was eventually forming a nuclear fusion reactor in space, turning hydrogen and helium into heavier elements. Lithium, carbon, nitrogen, oxygen, and around 20 other elements were created in the core of the first stars. Iron is the heaviest element that can be formed in this way. Heavier elements like gold are formed in the supernova explosions of huge stars, and this is why they are so rare in the universe. The universe began to light up, and stars, under gravity, started to come together, and galaxies started to form, as hundreds, then thousands, then millions, and then billions of stars began to orbit each other. Galaxies are where most stars live, and are centered on a galactic core. In the middle of each galactic core, we find a supermassive black hole. But let's come back closer to home for now. What about our solar system, our cosmic backyard? The solar system formed around 4.6 billion years ago, and, just like before, it started with a huge cloud of hydrogen in a nebula somewhere. But because our Sun was not a first-generation star, there were some other elements in this cloud, although it was still mostly hydrogen and helium. Over time, gravity pulled the cloud together and it got hotter and denser and it started to spin. Eventually, it got so dense in the center that the Sun was born, and the leftover material was a hot spinning disk around it. This disk condensed under gravity into belts, and then it started to ball together into spheres, so that eventually these rings around the Sun would clump together to form all of the solar system bodies, all of the planets that we are familiar with. So, bluntly, how the hell do we know, or think we know, all of this? Well, this is one reason. This is the Hubble Space Telescope, and it has been one of our greatest champions for discovering the cosmos. It was launched in 1990, and it can see much further and much deeper because there is no atmosphere to look through. Of course, we still use telescopes on Earth because we can build them so much bigger, and that helps. But when you don't have to look through the atmosphere, you can see things that you just can't see from the Earth's surface. Hubble is getting quite old now, and it's due to be replaced by the James Webb Telescope, which is due to be launched very soon at the time of recording. But Hubble will still be useful, and it could be looking out at the universe until 2030 or even beyond. So we're going to look quickly at some of the evidence we have for the Big Bang and the model of the universe we have built from it. Now, these pieces of evidence come together to make a picture, but there is no silver bullet piece of evidence that proves the Big Bang completely. And of course, we are going to look at all of these things very, very quickly and skip over a lot of detail. We are fairly sure that something happened 13.7 billion years ago, but we haven't fully demonstrated exactly what it was. One thing we do know is that the universe is expanding, and it was Hubble, the man, not the telescope, that showed us this using something called redshift. Edwin Hubble measured that most galaxies are moving away from us and each other, and in fact, the further away they are, the faster they seem to be moving. He did this using an effect called redshift. What is that? You may know that white light is made up of all the other colors of light, and the color of light depends on its wavelength. Red light has a longer wavelength than blue light. You may not know that light waves can be stretched as they travel through space, and if they are stretched, they are going to get longer, and that means they are going to become more red. That might be a hard idea to get your head round, but there is a good real-world example that uses sound: the Doppler effect. If you've ever been on the street while a police car passes you with its sirens going, you will notice the noise changes as it goes past. The sound actually gets lower when the car goes past. This is because sound waves are affected by movement. Look at the diagrams below. In the diagram on the left, you can see that a stationary object emits sound equally in all directions. On the right, you can see as the object moves, the sound waves in front of the object are squeezed closer because the sound catches up with itself. Behind the object, the waves are stretched out and the wavelength gets longer. Sound waves at a longer wavelength are lower, and that is why the police car sound gets lower when it goes past you. The same thing happens with light, but when light is stretched to a longer wavelength, it gets redder, and we can detect this with our telescopes. So when objects are moving away from us, the light gets stretched, and so they seem redder. We don't have a really intuitive understanding of this because we can't see this effect at normal speeds. We didn't even discover the Doppler effect until we could make things that moved fast enough for us to hear the sound change. And the redshift effect is far too small for us to see at normal speeds and distances. Another piece of evidence for the Big Bang comes from the background radiation, the oldest light in the universe. This comes from the epoch of recombination, when atoms first formed. You may remember that plasma became matter, and that meant that photons stopped interacting and began to fly straight through the universe. Some of those photons are still traveling now, and we can detect how long they've been traveling. We can tell that they were once very high energy photons that have been dimmed over the course of their journey by redshift. Quasars is a very sci-fi sounding name. What are these objects? Well, they are galactic cores that are very highly active. They are as big as our whole solar system, and they put out more light than the rest of their galaxy combined. We can see by looking out at the universe that quasars were more common in the early universe, And this showed that the universe is changing over time. A long time ago there were more quasars, and now there are fewer. This was not so much evidence for the Big Bang, but it was evidence against its main competitor, the steady-state universe, the idea that the universe stayed the same over all time. We can also look at radioactive decay. We know that radioactive elements decay at a predictable rate, and so we can tell how old rocks are. And moon rocks have been found and dated to be older than the Earth. And so we do have some confidence that the formation of the solar system is about the same age that we have calculated, 4.6 billion years. We know that the Sun was not a first-generation star, and so with the timeline that's emerging from radioactive decay, we see the picture seems to be consistent with our model of the Big Bang around 13.7 billion years ago. The evidence from radioactive decay fits nicely together with our theories of stellar formation and evolution. We observe the life cycle of stars, or rather we observe different stars in different stages of their life cycle, and we start to understand how this might change the development of the universe, and what that might tell us about the age of the universe. Our current models of stellar evolution show that the generations of stars seem to match up with our expectations, and again we are building a general picture of a universe that is around the age that we expect. We can also build the speed of light into our model. The speed of light is a universal constant that we know, around 300,000 kilometers per second. And we can use light to observe stars millions or billions of light years away. A light year is the distance that light travels in one Earth year. So if a star is 500 light years away, the light you see today left the star 500 years ago. Those photons have taken 500 years to get here, and so you are really looking back in time when you look at the stars furthest away. The furthest stars that we can see are 10 to 15 billion light years away. And we do have equipment that should be able to see further than that, but there is nothing viewable. Do notice that it's important to say that doesn't mean that there isn't anything there. What we can see is simply called the observable universe, but the universe could be much bigger than that. The problem is that light can only have been traveling since the era of recombination. And so that tells us that if the farthest stars we can see are 10 to 15 billion light years away, that means that the light from them has only had a maximum of 10 to 15 billion years to travel here. Anything further than that might be out there, but it is not possible to see it because there has not been time in the universe for the light to get to us. So that is the end of our brief look at cosmology, but I'd like to finish on the background, which is a section of the Hubble Ultra Deep Field. Back in the early days, we were testing out the Hubble telescope, and as one of the tests, we took it and pointed it at a part of the sky that was as dark as possible. And this is what it saw. Just to say that again, we pointed it at a part of the sky where we thought, with all of our earlier telescopes, there was absolutely nothing there. As you can see, that simply was not true. And I also want to point out that everything on this picture is not a star, it is a galaxy. Some of the things are very clearly galaxies, but even those very, very tiny points of light on the picture, those are not stars, those are whole galaxies, each made up of billions or even trillions of stars. By the 1990s, we knew the universe was big, but Hubble helps us to see exactly how big it really was. Astronomers at the time were completely blown away by this, and so I hope that you've been blown away a little bit by it, and I hope that you've learned something in our time here. Thank you for watching. If you have enjoyed it, then please like the video, subscribe to our channel, and maybe pass it on to a friend who might also be interested in learning about cosmology. Thanks again for watching, and bye for now.